Guys, so today we're going to be in section 5, or really chapter 5, section 1. So the first section of chapter 5, which is systems of linear equations in two variables. So we are going to dive right in. Before we learn how to do, how to solve systems of equations, the first thing we're going to do is to determine if a given ordered pair is a solution to a system of equations. So let me show you what a system of equations looks like. A system of equations is simply two equations joined together with a curly bracket on one side, and we call that a system of equations. What that means is we are looking for a solution that satisfies both the top equation and the bottom equation. If the solution that they give us only works for one of them and not the other, then it's not a solution for the set. And so we want it to work for both. And so when we are determining if an ordered pair is a solution to a system of equations, we have to plug the given ordered pair into both equations and make sure they both work. So for this first one, we have the ordered pair of 4, -1. So I'm going to plug that into my top equation. Everywhere there's an x, I'm going to put a 4. Everywhere there's a y, I'm going to put a -1. So I get 4 minus 2 equals 2, and I get 2 equals 2. That's good. That means that that ordered pair was a solution to the top equation. But I've got to do it again for the bottom equation. So again, anywhere there's an x, I'm going to put a 4. Anywhere there's a y, I'm going to put a -1. I get 4, a -2 times a -1 will be a +2. 6 equals 6. Check mark again. So this is a solution. The 4, -1 is the solution to the system of equations. Okay, but what about if it's -4, 3? Is this a solution to the system of equations? Again, we're going to do the same process. Anywhere there's an x, I'm writing -4. Anywhere there's a y, I'm writing 3. -4 plus 6 equals -2. I get -2 equals -2. So it works in the top equation. We're halfway there. -4 minus 2 times 3 equals 6. -4 minus 6 equals 6. I get -10 equals 6. Is that true? Does -10 equals 6? Nope, that's false. So this is not a solution to the system of equations. So these are plug and chug problems. The difference is you have to plug and chug into two different equations instead of just one, like we did with a linear equation. I am going to screen share you my notes for the next thing. When we solve systems of equations, there's two different methods we're going to learn. We're going to learn how to solve them using the substitution method, and we're going to learn how to solve them using the addition method. So the substitution method is the first one. What we have to do first is we have to solve one of our equations for one of the variables. It means we either have to get x all by itself or we have to get y all by itself for one of our equations in our system. Then we're going to plug that into our other equation, solve for the remaining variable, substitute that answer into the original equation, and solve for the last variable. This will make more sense when I do an example here in just a moment. The last step will always be to check your solution. If you pull up my notes, like my paper notes, this one that I have pulled up for you, if you pull that up, I check all of the solutions. I'm not going to check them all on the board just for space and time reasoning, but you should check all your solutions. So here we have an example for our system of equations. And I'm going to leave the substitution method up, the steps, so that you can see how we work through it. And then when we move on to the next one, I may close that down. But our example is 5x minus 4y equals 9 and x minus 2y equals -3. That is our system. So we want to isolate one of the variables in one of these equations. And so I always ask, which variable is the easiest one to isolate? Well, if you look at the second equation, we have an x minus 2y equals a negative 3. This x doesn't have a coefficient. It doesn't have anything connected to it, so that's probably the easiest one to isolate. So I would add the 2y over. So I get x equals 2y minus 3. Now I have this x isolated. So now I can take this 2y minus 3 and I can plug it into the top equation in place of that x. That's why it's called substitution. Step 2 says plug that into the other equation. So I have 5 times x, but instead of writing x, I'm going to do 2y minus 3 minus 4y equals 9. I'm going to distribute. So I have 10y minus 15 minus 4y equals 9. Combine my like terms, so I get 6y. And I'm going to go ahead and add that 15 over, which will be 24. Divide both sides by 6, and I get y equals 4. That's half of my solution. That's the y value. Now, in order to get my x value, I'm going to take this and plug it in right there where I had my x. Because I said x equals 2y minus 3. Well, now that I know what my y value is, I can just plug that in and chug out my x value. So that's 2 times 4 minus 3, which equals 8 minus 3, which equals 5. So my x value was 5 and my y value was 4. This ordered pair is a solution to my system. And if I plug both of those values back into both of the original equations and check them, they do check and they do hold that they are both solutions. Let me stop the sharing and we'll do another example. So for this example, we have 3x plus 2y equals 4. And then we have 2x plus y equals 1. So again, I'm looking for which variable is going to be the easiest one to isolate. And the y on the second one is going to be the easiest. So I'm going to subtract that 2x over so that y equals a minus 2x plus 1. And again, I'm going to plug all of that into the first equation in place of y this time. So I have 3x plus 2, and then instead of y, I'm going to plug in minus 2x plus 1 equals 4. I'm going to distribute that 2. I'm going to combine my x's on this side. I'm going to subtract over that 2. So I get x equals negative 2. Now I'm going to plug that in to my y equals equation. I have y equals negative 2x plus 1. Well, I found out my x is negative 2. Negative 2 times negative 2 is a positive 4. So I get y equals 5. So my ordered pair would be negative 2, comma 5. Plug that solution into both of those equations and check it. It will come up and it does work. So that is the substitution method. You solve one of the equations for one of the variables, and then you plug it into the other equation, and then you solve for the remaining variable, substitute the answer into the original, and then solve for the last variable. So that's substitution. We substitute things in. Okay. There's also another method called the addition method. This is the one I feel like we use more. Although, I mean, I'm only going to use a couple examples of both, but either one will work no matter what system you're dealing with. It's just sometimes it's nicer to use substitution method and sometimes it's nicer to use the addition method. So the addition method, you have to get both of your equations in general form of ax plus by equals c. Then we are going to multiply one or both of the equations so as to eliminate one of the variables when we add them together. I'll show you what that means. We're going to solve for the remaining variable, then we back substitute. We take that value and substitute it into one of the original equations and solve for the last variable. We back substituted here in our substitution method because we got x equals something, and then we back substituted that into the original equation and solved. So you're still going to do that step even in the addition method. It's the steps before we get that solution that are different. Okay, so we have 3x plus 2y equals 48, and we have 9x plus minus 8y equals a minus 24. So if I drew a big line underneath this and I added these together, I wouldn't eliminate any of my variables. And so I can't do the addition method yet because it's not going to eliminate anything. So I need to either eliminate my x's or I need to eliminate my y's. It does not matter which one you choose. It will work no matter what. For this example, I did choose to eliminate my x's. So I'm looking at 3x and 9x. Is there something that I can multiply one of these equations by so that if I add 3x and 9x together, that's going to go away? Yes, if I multiply this top equation by -3, that'll give me a minus 9x. And then that's a positive 9x, which means my x's are going to go to 0. That's what we're trying to do with the addition method. So I'm going to write underneath the second equation, I'm going to write the top equation, but everything times -3. So that's minus 9x minus 6y equals a minus 144. Then I'm going to draw a big line and a big addition symbol. Now I have 9x minus 9. Those go away. That's the whole point. We wanted one of our variables to go away. 11. -8 minus 6 is a minus 14y, and a -24 and a -144 is a -168. I'm going to divide both sides by a -14, and I get y equals 12. From this point on, it's exactly like the substitution method. I got a value for my y, so I'm going to plug that into one of my equations up top. It doesn't matter which one. I'm going to plug it into the first one. So I have 3x plus 2y equals 48. I have 3x plus 2 times 12 equals 48. 3x plus 24 equals 48. I get 3x equals 24, so x equals 8. So my ordered pair is 8, 12. So the thinking about how to eliminate one of your variables is the tricky part. Would I have gotten the same solution if I had eliminated my y's first? Yes, I would have. I would have just gotten x equal 8 first, and then I would have back substituted to get the y equals 12. Either way totally works. It doesn't change any of it, so don't worry about that. Okay? Again, you should check your solutions. But I did that on the notes page, so you can stop and see that there if you want to. Let's do another system of equations using the addition method. We have 2x equals 7y minus 17. And then we have 5y equals 17 minus 3x. Excuse me. So the first thing is we need to get our x's and our y's on the same side. So I'm going to have 2x, and I'm going to subtract that 7y over. And for the bottom equation, I need to get this negative 3x over, so I'm going to add 3x. So there's the system of equations written in the ax plus by equals c form. Now, I need to eliminate one of my variables. I need to eliminate either my x or my y. But neither of these is like as nice. On the other one, I just had to multiply the top equation by a negative 3, and then it eliminated both equations. In this case, that's not going to work because I have a 2x and a 3x, and then I have a negative 7y and a positive 5y. So none of those are factors of each other or multiples of each other. So what I need to do is I need to think, what can I do to both equations? So basically, you just need to pick one of your variables that you want to eliminate. I'm going to eliminate x. So I'm going to multiply this top equation by a minus 3. Since both of them are positive, I'm going to have to multiply one of them by a negative number so that when I add them together, it goes away. And then I'm going to multiply this bottom one by a positive 2. So I looked at the coefficients and I'm just multiplying the equations by the coefficients, but I did put a negative on the top one. So I will have negative 6x plus 21y equals a positive 51, because I had a negative 17 times a negative 3. Then I have a positive 6x plus 10y equals 34. Draw my line. I'm adding these together. I have a minus 6x and a positive 6x. Those go away. 21y plus 10y equals 31y equals 85. So y equals 85 over 31. 31 is a prime number, so I know I can't reduce that down. It's not a multiple of 85. That's it. I mean, you might get fractions, and that's okay. Do we like fractions? Not always, but that's also okay. So now I'm going to plug that into one of the solutions. It doesn't matter which, or one of the equations. I plugged it into the top one. If you plugged it into the second one, it's still going to work. I do just say be careful because you are dealing with kind of a yucky fraction. So I have 2x equals 7 times our y, which is 85 over 31, minus 17. So I'm going to multiply. I have 2x. 85 times 7 is 595 all over 31 minus 17. We need to get that 17 to have a common denominator with the 31. To do that, I'm going to have to multiply the top and the bottom by 31. So I get 595 over 31 minus 17 times 31 is 527 over 31. So 2x equals, I subtract those, I get 68 over 31. Now I'm dividing by 2, or you can think about that as multiplying everything by a half. That'll eliminate the coefficient. I'm left with x equals, and then when you multiply, you can simplify that down. So that's 34 on top. 34 over 31 is my x. So even though they're not nice numbers, those are the solutions. And you get 34 over 31, comma, 85 over 31. So please don't be scared if you get what I call yucky fractions. It doesn't mean it's wrong. It just means that this problem has yucky fractions. That is the addition method. So far, every time we've done a system of equations, we've gotten an ordered pair. We've gotten a solution. But really, when we solve systems of equations, there's 3 options that we can get. there's the option that we've been getting where we have exactly one solution. That's where our two lines intersect at only one point. And that one point has been the ordered pair solution that we've been getting. However, we could also have no solutions. If our lines are parallel to each other, then they're never going to cross and we're never going to get a solution. There's also where we could have infinitely many solutions. So it might be kind of hard to tell, but I have a long line and then I have like a short line that's sitting directly on top of that line. That means that these lines are multiples of each other, which means they share all of the exact same values. And so that means there's infinitely many solutions for that system. So we're going to do two more examples so that you can see an example of a no solution system and an infinitely many solution system. You've had tons of examples of an absolute, like a single solution. So these two examples will show you what the other two are doing. This first system, I have 4x plus 6y equals 12 and 6x plus 9y equals 12. So for this one, I'm going to do the addition method, and I'm going to try and get rid of my x's. So I have 4 and 6. What do 4 and 6 both go into? Well, they both go into 12, right? So I'm going to make one of them positive and one of them negative. So to get a 12 on top, I have to multiply by 3. And to get a 12 on bottom, I'm going to multiply by a -2. That way, when I add them together, they go away. So I have 4x times 3. That'll be 12x plus 18y equals 36. Now on bottom, I have a minus 12x minus 18y equals minus 24. Draw my line. I'm going to add them together. 12x minus 12x, 18y minus 18y. Uh-oh, everything goes away. That's okay, but I have 0 equals 36 minus 24, which is 12. Does 0 equal 12? No, it doesn't. This is a false statement. And if you get a false statement, that means that there's no solutions. So this is one of those times where we have two lines that are parallel to each other. And so they're never going to cross, so you're never going to get an ordered pair solution. For our second example, we have y equals 3x minus 2, and we have 15x minus 5y equals 10. Since the first equation is already a y equals equation, I'm going to use the substitution method. So I'm going to take all of this and plug it in for my y in my second equation. So I have 15x minus 5 times 3x minus 2 equals 10. I'm going to distribute my 5. So 15x minus 15x plus 10 equals 10. Notice I have 15x minus 15x, so that's going to go away. So I'm left with 10 equals 10. Is that true? 10 equals 10. Yeah, that's always true. And since it's always true, that means there's infinitely many solutions. This is the graph where the lines are on top of each other. So there's not a value for x that you can come up with that's going to make it not work because they all have the same values. Okay, we're going to do one more problem because we've encountered this problem before back when we did word problems, but now we can solve it using a system of equations. And so for some people, this way is like they really enjoy this way with the systems over the other method that we used earlier in the semester. So I always like to show it. This is our mixture problem. Let me go over to the book. So in the book, right here, we have a mixture problem. This is page 552 in your book. I say that on the notes page in case you want to open it up yourself. So it says a chemist is working on a flu vaccine that needs to mix a 10% sodium iodine solution with a 60% sodium iodine solution to obtain 50 milliliters of a 30% sodium iodine solution. How many milliliters of each of the 10% solution and of the 60% solution should be mixed? So I always take notes when I read those problems. So for me, it says that we're going to have a 10% solution and we're going to have a 60% solution that we combine together to get 50 milliliters of a 30% solution. Like, that's just the general information that I get from the problem. It wants to know how many milliliters of the 10% solution I need and how many milliliters of the 60% solution I need. So the way I would do this is we need to just say, we're going to let X equal the number of milliliters of the 10% solution, because we don't know what that is, so we're going to call it X. And then we're going to let Y equal the number of milliliters of the 60% solution. We don't know what either of those values are, but we're going to let them equal, like let X equal the number of milliliters 10, let Y equal the number of milliliters of 60. Now here's where we're going to get our first equation for our system of equations. What do we know about the number of milliliters total? Well, if we're mixing our 10% solution with our 60% solution, we're going to get our 30% solution at the end. And we know we're going to get 50 milliliters of it at the end. So if we take the number of milliliters of our 10% plus the number of milliliters of our 60%, we're going to get the number of milliliters of our 30%, which is 50. So right there we have one equation for our system of equations. Now, what about the rest? Well, we have strengths. I did a table previously for how we did these, but it's really the same method, what we're doing. Okay, we have 10% solution of our X, so 0.10 of our X, plus 0.60 of our Y, I'm just adding our strengths to this, equals 0.30 of our 50. Right here is our system of equations. Now, obviously, we can simplify this down a little bit before we do anything else with it, but we have our system. We have our two equations, two unknowns. This one deals with the amounts. This one deals with the strengths. We have X plus Y equals 50, and then we have 0.10X plus 0.60Y equals, and then 30, the 0.3 times the 50 equals 15. Now you can use the addition method or you can use the substitution method. Since our top equation is so nice, I'm going to solve for one of my variables and do the substitution method. I'm going to say X equals 50 minus Y, and then I'm going to plug that into my second equation in terms of X. So I get 0.10 times the 50 minus Y plus 0.60Y equals 15. I'm going to distribute that, the 0.10. So that'll be 5 minus 0.10Y plus 0.60Y equals 15. I'm going to combine my Y's where I have 0.5Y. Subtract this 5 over to get 10. Divide both sides by the 0.5, and I get Y equals 20. Now, what was Y? Y was the number of milliliters of the 60%. Now that we know what our Y is, we can plug that in to find out what our X is. X equaled 50 minus Y, 50 minus 20, so X equals 30. And that was milliliters of 10%. When we did this problem previously, we did a table, but we still came up really with the same thing. The only thing that we did differently is we didn't call it X and Y. And the reason we didn't is because we didn't know how to solve systems of equations yet. What we did is we kind of jumped right to this step. And instead of saying X, we would have said it in terms of 50 minus Y. So it's the exact same process that we did, and we're getting the exact same solutions. So if previously with the table, if that method works best for you, then still use that method. Don't feel like you have to use the system of equations in order to solve this mixture problem. You can do it the exact same way that we did it before. If this makes more sense because you're like, yes, there's two things and then there's X and Y and I can substitute it and do it that way, do it that way. Either way is correct. Either way will get you the solution if you do the math right. So that is the end of 5.1.